Welcome. Now we'll discuss modes of heat transfer. You know heat and work, which you have studied in engineering thermodynamics. Heat and work are the energy in transit having unit joule per second, that is watt. In thermodynamics, interaction between heat and work were studied, but rate of heat transfer and the time required for particular heat transfer and the estimation of quantity of heat transfer were not studied. The main objective of heat transfer course are to study the temperature distribution in a thermal system and to estimate the rate of heat transfer in thermal equipment or thermal system and the time required to transfer particular amount of heat. Temperature difference is the driving force for heat transfer. Means heat is transferred from higher temperature to lower temperature. Fluid is flowing from higher pressure to lower pressure. So pressure difference is the driving force for fluid flow. And for current flow, the potential difference is a driving force. So similar to fluid flow and current flow, we have heat transfer rate and the driving force is temperature difference. There are wide variety of application of heat transfer in thermal systems and equipments like boiler, furnaces, heat exchangers, solar energy, refrigeration and air conditioning systems, thermal equipment. Heat transfer occur by three modes: conduction, convection and radiation. First we'll discuss conduction. In conduction, heat transfer in material takes place due to molecular interactions. Heat is conducted from molecule to molecule by combination of following two mechanisms. Let us consider metal rod inserted in a furnace or fire. Then other end of metal rod is also get heated, and in metal rod the heat transfer is purely due to conduction mode. The conduction takes place by two mechanisms: the drift of free electrons and lattice vibration. All matters is made up of or composed of molecules and atoms consisting of proton and neutron at center called as nucleus and the number of electrons revolving around the nucleus in orbits. In most of the metals, the number of electrons are more than the proton, and that extra electron are called as free electrons. And the free electrons have a ability to move from atom to atom and conduct the heat and electricity. So more are the free electrons in the atom, the material is more conductive. So free electrons move from atom to atom and conduct the heat. So we can say good conductor of electricity is also good conductor of heat. Both heat and electricity are conducted by the free electrons in metals. Second mechanism is a lattice vibration. Heat conduction due to restricted motion of molecules within the material. The material may be solid, liquid or gas. Means the molecule and atom of all matters vibrate or oscillate in a definite frequency with a definite magnitude. And due to this vibration or oscillation, heat energy is transferred. Heat is conducted through the material, and this mode of conduction is more dominant in non-metals. In metals, mainly heat conduction takes place by drift of free electrons, and in non-metals, mainly heat transfer takes place by lattice vibration. Now we'll discuss the law which governs the heat conduction, and it is Fourier's law of conduction. It states that the rate of heat transfer is directly proportional to temperature gradient and area normal to direction of heat transfer. Mathematically, Fourier's law of conduction gives heat transfer rate Q is directly proportional to minus A dt by dx. Here minus sign is there because heat is flowing in a decreasing temperature direction. Now, including the proportionality constant K, we have equation of heat transfer by conduction Q equal to minus Ka dt by dx. Consider a plane wall of thickness L, whose one side is at temperature T1, other side is at temperature T2, and heat flowing through the wall is Q in this direction. Then A is the area normal to heat flow direction. So heat transfer Q by conduction through the plane wall is given by equation Q is equal to Ka T1 minus T2 by L. So for plane wall, T1 minus T2 by L is the temperature gradient. In this equation, Q is heat transfer rate in watt, K is thermal conductivity in watt per meter per Kelvin, which is a property of a material, and it gives ability of material to conduct heat. And thermal conductivity is defined as a ratio of heat transfer to product of area and temperature gradient, or in other words, it is the rate of heat transfer per unit area per unit temperature gradient. So dt by dx is the temperature gradient in degrees Celsius per meter or Kelvin per meter. T1 and T2 temperature of surfaces in degrees Celsius or Kelvin. A area normal to direction of heat conduction in square meter. L is the thickness of wall in meter. Small q is equal to ratio of heat transfer to area. That is, heat transfer per unit area is called as heat flux, whose unit is watt per square meter. Second mode of heat transfer is convection. In convection, heat transfer is due to bulk motion of fluid, which is because of buoyancy effect produced by temperature difference or by external aids like fan, pump, blower, or wind. Convection are of two types, natural convection and forced convection. In natural convection, convective currents are set up due to buoyancy effect, which is created due to density difference, and density difference is caused due to temperature difference between the surface and fluid. The fluid is moving and transfer heat due to density difference. The heat is transferred from surface to the fluid when the surface is hot and fluid is cold, and heat is transferred by natural convection from fluid to surface when fluid is hot and surface is cool. Second mode of convection is forced convection, in which the fluid is moving due to external aids like fan, pump, wind. Example is heat transfer in heat exchangers, in which the hot and cold fluids are circulated by pump, and when wind is blowing over the hot body and the body transfer heat, that is also example of forced convection. An example of natural convection is the cooling of hot body in still air. The heat transfer in convection is given by Newton's law of cooling, which states that the heat transfer by convection is directly proportional to temperature excess and area of surface. Mathematically, Newton's law of cooling is given as heat transfer rate Q is directly proportional to surface area of plate or body into wall temperature minus fluid temperature. Introducing proportionality constant H, we have equation Q equal to HA TW minus T infinity, which gives the heat transfer by convection, where Q is a convective heat transfer rate in watt, A is the area of surface which is in contact with the fluid. Area in Fourier law is the area normal to the heat flow direction. Here area is the surface area which is in contact with the fluid. TW is the wall or surface temperature. T infinity fluid temperature. H convective heat transfer coefficient in watt per meter square per Kelvin. Convective heat transfer coefficient is a very complicated complex parameter in heat transfer and is a function of geometry, fluid properties and flow properties. So there is no specific relation or formula to determine H, but we have number of thousands of correlation for different fluid property, flow properties and geometries. So convective heat transfer coefficient H is a function of temperature, length means area or geometry, then mu viscosity, rho density, K thermal conductivity, Cp specific heat, U velocity. So H is function of number of parameters. Now we'll discuss third mode of heat transfer, radiation. Any body having temperature more than zero absolute temperature radiate energy, and it mainly depend upon absolute temperature and surface area. The energy radiated by a body is travel in the form of electromagnetic waves according to Maxwell theory. And according to Planck's hypothesis, the energy radiated by the body is a travel in the form of teeny particles called as photons. Both theories are equally accepted. The body having more temperature radiate more energy. Body having low temperature radiate less energy. And the energy radiated by body is given by Stefan Boltzmann law. And it states that heat energy radiated by body per unit area is directly proportional to fourth power of its absolute temperature. Mathematically, it is given as below. Energy radiated Q is directly proportional to T raised to 4. So, energy radiated per unit area Q is equal to energy radiated upon area. Introducing proportionality constant sigma, we have Q equal to sigma T raised to 4 is called as Stefan Boltzmann law, and the energy radiated is simply Q equal to sigma A T raised to 4, where small q is the heat energy radiated per unit area of a black body. A area of surface in square meter. Sigma Stefan Boltzmann constant in watt per meter square per K raised to 4. T absolute temperature in Kelvin. The body having more temperature radiate more energy according to Stefan Boltzmann law, and the body having low temperature radiate less. The energy radiated by a high temperature falls on the low temperature body, and the energy radiated by low temperature body falls on high temperature body. The net effect is the heat energy gained by the cold body and heat energy lost by the hot body, and the net heat transfer by radiation between the two black bodies at higher temperature and lower temperature, that is body 1, which is at temperature T1, and body 2 at temperature T2, is given by Q12 net heat transfer equal to sigma A T1 raised to 4 minus T2 raised to 4. This gives the net heat transfer by radiation between the black bodies. And for real surfaces, the one more parameter is introduced, and this heat transfer rate is multiplied by emissivity. The heat transfer in thermal equipment are not only by any single mode, that is conduction or convection or radiation, but also combination of two modes or all modes. Here let us consider steam pipe, and steam is flowing through the pipe at high temperature. So heat of steam is transferred to the inside of the pipe by convection. Then heat is conducted through the wall of the pipe and appear on outer surface of the pipe, and then it is lost to the surrounding by radiation and convection. So in this problem, heat is transferred from steam to inner surface by convection, then heat is conducted through the wall, and heat is lost to the surrounding by convection and radiation. So all three modes are involved in this heat transfer problem of steam pipe. Similarly, we have another example is furnace. In furnace, the steel stock is heated by burning fossil fuel or by producing heat by electrical heater. Then heat issued by the stock is by convection and radiation, and furnaces are operating at high temperature. So the main component of heat transfer is radiation mode, and less heat is transferred by convection. So for this steam pipe, heat lost to the surrounding is simply the sum of heat loss by convection and heat loss by radiation. Heat transfer by convection and heat transfer by conduction required material or medium. But radiation does not require medium for exchange of heat. In first two, in convection and radiation, heat transfer is directly proportional to temperature difference or directly proportional to temperature. In radiation, heat transfer is directly proportional to 4 power of absolute temperature. So at low temperature, radiation is negligible, but at high temperature, it increases very rapidly. So in case of furnace, the main or a dominant component of heat transfer is radiation. So up to temperature of 150 to 200 degrees Celsius, heat transfer by radiation in some cases, for simplicity, it is neglected. But for higher temperature, we cannot neglect radiation, and after 400, 500, it become major component for heat transfer. Thank you. If you have any query, mail me on hdbharati@kkwa.edu.in.